the original plan for today is to do, basically to kind of go over what was talked about in lecture. But there are also a number of people who asked me to do a little bit more assembly stuff. So what we're going to do is we're going to try to do a little bit of both. So the first thing is, how do we want to talk about the register file, how that actually works, because this is a nice system. It's fairly simple, and it's got a lot of concepts that show up in a lot of other places. So one of the things we need to talk about is the register, or rather a single register with an enable. I don't know if I'm drawing it exactly the way it is on the handout.
Yeah.
That is? Okay.
Well,
So
that's actually called D and Q.
Yeah. Data and Q just means output.
Yeah.
I'm not sure what
Gil even said there's no reason why it's Q.
yeah, but it's always Q. So, and this is actually called a DQ register. I don't know. There's something about Q they like.
O was already used for something else, and they stuck a little hash in it, and then realized
Maybe.
it was a Q.
Maybe. Computer scientists get a little weird when they do things. Okay, so if we want a one register file, we're done. Right? This thing does everything we want. We put 32 bits in here. We take 32 bits out of here, and we have our enable. This would be WRF. And there's our one register file. And basically it just operates by, there's a value sitting here. We say, and there's a clock. I'll say this a lot. I'll say it's sitting here, but there's a value on the wires here. So some wires have a higher volt, are at 5 volts. Some wires are at 0.
Because we typed it in.
Because it's connected to the output of some other device. There's some lot here. One of my blob logic things. That is outputting a value, and what we're going to do is we want to grab that value and hold, or we may or may not want to grab the value and hold on to it. And the way we decide whether or not to grab it is this enable line, WRF.
Remind me what WRF stands for.
Write enable register file. Okay. So the value comes in here, and if it's time to grab it in here, we'll raise WRF. We'll make it be 1. The value will come in, and when on the next clock tick, the value of the input will be asserted on the output. Okay. If we lower WRF, if we make it 0, we deactivate it. Then whatever value is currently on the output will remain on the output until we load a new value in. Does this make sense to all you guys? Okay, good. Because this is yes.
We talked about in lecture how how bits are stored and capacitors on main memory. Is it a different?
It's different here. There are gates inside this one. This is a significant. We actually have. I believe we have a lecture coming up that's pretty much devoted to these guys, because they're an extremely important device, and it's a kind of interesting how they do it. That's going to get a little annoying after a while. Yeah, hopefully. All right. Well, I'll try talking louder, and we'll try to keep going. Oh, I can talk quieter now. All right. So this is a register, and it's as I said, it's a very important building block for our computers. It's not to be confused with memory, but these guys are very quick, which is very important, whereas memory is generally not. This is in terms of computer speed. So memory takes 100 nanoseconds to access. you can get a value out of this guy in about 2 nanoseconds, maybe less. Actually, better. Sorry, that's probably an old number, so it's probably less than a nanosecond now easily. But it comes out fast, and we can load things into them, and we can take things out of them. Right now, how do we turn this into a 32-bit register file, or a register file with 32 registers in it? Actually, let's not try so hard. Let's turn it into a register file with 4 registers in it, so I can actually draw the entire circuit on the board.
Registers aren't a form of memory?
They are, in a way. I mean, they have state. They store things. So in that sense, yes. We generally reserve the word memory for the bigger, slower types, and we just call these guys registers. Because these guys tend to be a little more intimately connected to the computation than a large memory. Right. See, we think about memory. We usually think about our main memory as like it's kind of off to the side, and our processor asks it for stuff. Whereas registers are, part of our processor. They're in there. They hold the state of the machine. So we generally kind of make that distinction, though of course it's an arbitrary one. Okay. So we're going to start by having 4 registers, which is precisely how many we need. And we have to figure out, well, how do we interconnect them all? See, this is why I didn't do 32 of them. Okay. Well, let's talk about the output. I want to be able to take. Pretend I have 4 values here. There's machinery missing over here, but I have 4 values here, and I want one of them. So suppose I want the second one of them. We got to figure out, well, how do we choose which one we want? And the other day, we talked a little bit about muxes, right? Muxes are big switches. So what we do is we just wire them all into one of these big switches. And this mux takes a 2-bit control signal. So you can give it the numbers 0 through 3. By the way, we're going to number our registers 0, 1, 2, 3. We always start with 0 in the computer. And basically, depending on which number we choose, we'll get the value out of that register. You guys all following this? Good.
So do all the registers send a signal to the mux and then just one gets chosen? Like sort
Right.
of late in there?
Well, so let's assume we're not writing because it simplifies things. Each of these registers is holding a value, and they're all they're all different. They're all unique.
While they're holding values, what happens when the clock ticks?
As long as the enable is off, nothing happens when the clock ticks. That is the important property. That's one of the 2 important properties. When the clock ticks and the enable's off, whatever the output used to be, it still is. So these devices are just sitting there and continually feeding out a signal. The mux here, though, decides which one of them gets to talk over here. No one else, only one of them gets switched in. And actually, on beta sim, it'll draw a line across like that. So if I want a number 2. That's what I said earlier. So if I want number 2, the mux is essentially, depending on what you put in here, so if I put a 2 in here, it'll connect this to that. Okay. Now keep in mind, we're talking about, I didn't actually talk about how many bits there are on each of these wires. It's actually, each bit looks like this. When I go like this, what I'm essentially saying is this whole circuit is replicated 32 times, and each bit is handled by one of those 32 circuits. Or kind of the other direction to look at it. Oh, in that direction, in that way of looking at it, each register holds 1 bit, and a value is stored by putting 32 little 1-bit registers next to each other. the sideways way of looking at it, if you feel more comfortable in that direction, is the register each register can hold 32 bits, and the mux can switch 32 bits, and we just have 32 wires. We'll choose whichever one. When we start building it, you'll have to worry more about these issues.
When we start with?
Building them.
How do you build them?
From Gates. It's
Using some software?
or on paper. They're not too complicated. One of the things that shows up a lot is it's just the same circuit replicated over and over again. These are actually fairly simple circuits. They're trying to think. I think about 6 NAND gates you can make these with, and this is a similar number, and a few inverters and a few other little pieces of logic. So there we have we now have a circuit for reading values out of here, right? So if I want the value that's stored in this register, I simply put a 0 in here, and out it pops. So this is what exactly does this represent down here? This input. You have an idea? In terms of kind of how we do it in the data.
It's the coming off of the instruction.
Right. This is a read address, right? Okay. Now let's do the right side. Now I'm going to skip the whole idea of having 2 read ports at the moment, and we'll go back to that. So on the right side, well, we're only ever going to put one value into this system at any given time, right? So we have a 32-bit value coming in. It's a value to be stored, and we'll put our little logic in here. This goes off to do some other computation. So we have a 32-bit value coming in. Now we want to take it and we want to put it into a specific register. Well, this time we're going to pretty much do the opposite of what we've done here. So this is a mux, this is a demux or a selector. Basically the way this works is one value comes in and it gets routed out to one of, in this case we're going to have 4, to one of 4 wires. Okay. But it's not going to choose to which register the value goes, because every register is going to see the same value. It's going to choose which register is turned on or told to hold the value. And then what we're going to do is we're going to just provide every register with the same value. I'll put the little dots in where they connect. All right. So I have one value coming in here. This, by the way, is worth. This is only one bit. So this side has a lot fewer wires. And again, this has, and by deduction, it should be able to figure out what this input is called. And this is the write address. Okay. So suppose we want to do a write. We want to write the number, 32 bits, but I'm going to write a smaller number than that. I'm going to write the number 31 into R2. Okay. So what do the signals have to be? Well, I put a 31 up here. Actually, maybe I should use a different number. 24. So that's not like any of the other numbers I wrote on the board so far. Put 24 up on these wires, right? So the binary representation of 24 is carried by these wires to every single register. We're gonna tell worth to be on because we're writing. So we're gonna put a 1 in here. Let me circle these. Looks like I'm getting too many numbers in here. And what do we put here? If we want to write into register 2. 2. That's very convenient. So what's going to happen? Well, here we're going to have a connection from this to number 2. And this 1 is going to flow into here. So this guy here is going to be enabled. So the next value on the next clock cycle, it's going to take the value of its input and move it to its output. But none of the other registers are. So actually, there's a
Nobody calls for the output, it's not going to put it out.
well, it does. It's always outputting something. It's just that if no one's asking for it, it doesn't get anywhere past this mux. So that's actually the way. That's something that the way you should think about logic in the computer is it's always doing something. Right? This doesn't know when it's needed or not. Its sole job is to make these wires have the number, or one of its jobs. Its job is to make these wires have the appropriate number. It might be that there's no one down the other end listening to the wire, but it's still outputting that number. It still has that as its output. And this mux decides which one actually goes beyond this stage. Now, actually, along with that, another thing you might want to ask is, what happens to this wire? Right? There's a property of the demultiplier that I didn't mention. And that's what happens when something's not selected. You should be able to deduce what this is supposed to be. Right. Anything that's not selected has to be 0. What about the thing that is selected? Right. It's not 1, it's whatever the input is. It could be 1, it could also be 0. You guys all see that? So if I put a 0 in for WRF, I can put a write address in here, and this wire is connected, but nothing happens anyway. And in fact, that's something that happens all the time, because every piece of logic in the machine is actually doing its job all the time. We just ignore a lot of it. Right? And when we do when we run things through BetaSim, it lights up the wires. But all those other wires that aren't actually being used, they have values on them, but they're usually junk. We have to be aware of that, because things don't just kind of go away when you're not looking at them. All right. So we have our mux, or sorry, our register file. And it does pretty much everything we want it to do, right? That's a big win. So let me take away the things that aren't part of our register file, and very quickly we'll just see how do we make it 2-port. So this is going to be read address 1, and this is actually really easy. We have all these values, and we have a selector for read address 1. All we have to do is put in read address 2 into another mux. This is going to be output 2. And just connect all these wires over. And this diagram is getting really messy really quickly. Okay. And we can make a 3-port register file, and a 4-port, and a 5-port. Reads are easy. Writes are hard. Having 2 writes is just, we're not going to do that. Yeah.
So what are the ports doing? Like, they sending the information somewhere else?
These?
The extra mux that you just drove.
Oh, this one?
Yeah.
Yeah. This becomes, we call this one RD1. This is RD2. Well, actually, we can just take a quick look. That's the easiest way. Oh well. We'll take a look at the real register file in the beta, and we can see that. Okay, so in our memory here. Oh yeah. Okay, and let me make a new I should save this without GCD in it. Okay, so let me make one that lights everything up. Okay, so, well, we don't have any real values here. But in this case, what we're doing, we're using both ports of the register file. So we have an address here. Actually, well, let's make it register 1, register 2. Okay. So register 0 is passed into port, the address for register 0, rather, is passed into port 1. And out of the bottom here comes the value that's stored in register 0. So that is this part of the register file at work. On the other side, we pass in the address 1 for register 1, and out this second port, the one that's here, we get the value for register 1. Now they both use the same set of registers, and that's very convenient because sometimes if I do R1 and R1, I really want to get the same value out of both of them. Right? And it works out nicely because on the read side, the values are all just sitting here. If we go inside the register file, we have access to all of them, and we just have to put in a selector for each time we want to read out of there. And each of these selectors is pretty much independent. On the right side, though, it's not so simple. Making a two write port register file involves all sorts of trouble because if you try to write twice to the same register, things obviously get a little ambiguous.
So that box represents all the
Right.
muxes together, right?
Yeah. Well, this square here.
Yeah.
Yeah. This is the mux. There's a 32-way mux for writing. There are 32 registers, and there are two 32-way. Sorry, this is not a mux. This is a demux. I used the wrong term. And there are two 32-way muxes for the two outputs.
And that's all represented by that box.
Yep, and that's all inside that box.
So RA1 and RA2 are those red lines coming down from the triangle.
Correct.
Right. Okay.
Yep. All right. So I think we're going to skip talking about memory, and we're going to talk about assembly instead, because that seems to be the popular way to go. There's a lot to erase here. Okay. So let's talk about how to write. Actually, let me really quickly change the machine here back to. So I guess it doesn't matter which one I use. Looking at programs, my stack is hiding. Okay, so we have our machine. So let's write a program for something. What do we want to write? We can write something simple. No, we can't.
I just want to check my work.
How about sum of squares? We can do that one. Plus times x times y. So you guys should all be familiar with this one. All right, so how do we write it? Well, first what I want to do is I want to make a distinction between what a procedure is and what a program is. Let me load a program. Oh, by the way, I put most of the sample code into the shared directory so that you guys don't have to carry around those printouts all the time. I'll use GCDI. Okay. So this is iterative. This is the iterative GCD program, and the reason I can say it's a program is because, well, we have a bunch of instructions up here to execute. quick terminology piece. This is a procedure. The stuff that's highlighted is not meant to be executed by itself. It's meant to be, procedures are called from programs. And you'll notice that a program does not have the procedural abstraction, doesn't have the calling discipline and stuff like that. Right? So let's write that procedure up there. By the way, this should be familiar to you guys from Scheme. When you write out a lambda, nothing happens because the lambda is a procedure. It's not until you apply the lambda that you've actually got something significant to execute. So let's start with a new program. So now, one of the things I want to show you guys here is that you can actually write procedures without programs. And the reason I want to do this is to separate the two parts of the calling convention. So we want to write sum squares, and call it sum s up here. So this is a callee, right? Or at least we're doing the right now we're doing the callee side of the contract. So what do I have to do first? Got to push the link pointer. Push the base pointer. We move the stack pointer into the base pointer so we can set up the base pointer for a frame. We got to get the arguments, right? Load, what's this? Base pointer -3. I always know where the arguments are. I'm going to put that into R1. Load, base pointer -4 is R2. So this is X. This is Y. Right?
We should be protecting the register.
Yeah, we have to go back and do that. I tend to do that later because it's hard to tell what you're going to use until you know. Actually, I do know though. I can see far enough ahead in my head that we only need to protect R1 and R2 because I'm gonna reuse them a little bit.
So isn't the conventional thing you always use R0 for the return value?
Yes, we always use R0, so we never protect R0 because then we'll just kind of throw our answer away at the end.
Would you use R0 for the answer?
Sorry.
I
Yeah.
didn't hear his statement.
Oh yeah, R0 is the place where we put our answer. It's part of our contract. So at the very end of our code, before we do the return, before we start doing the return, we need to make sure that the correct answer is in R0.
Well, what about if you don't have a return value? Is it bad to use R0?
Then you no, it's not. The contract doesn't guarantee anything in that case. If you don't have a return value, it doesn't matter what you return in R0.
Yeah, but what's the convention?
At that point, there is no convention. It's not covered. The rule though is that the caller should assume if the caller calls something that doesn't return a value, whatever is sitting in R0 is garbage. You don't use it for anything. Even if you left something there, you have absolutely no guarantees to what's in there. So you assume there's nothing in there or nothing useful in there.
Save it yourself if you need it.
Yeah, save it yourself if you need it. All right, so let's do the square. We just multiply R1 times R1. I'm going to put it back in R1. That looks kind of weird, but it works. Right. So R1 has gone from being the place where we store X to the place where we store X squared. Well, R2, this is similar. R2 becomes the place where we store Y squared. And then we add R1 and R2 and put them in R0 because that's our answer now. And we're going to put our answer in R0. Now we're done, pretty much, right? Now we have to finish off. Now we have to satisfy the rest of our contract. We have to put back R1 and R2 because we messed them up. That's not push. Pop. And make sure you get the order right. If I were to pop R1 before R2, I would get them reversed. Last thing on is the first thing off. Move SP back, or move BP back to SP. Pop BP. And basically this is just copying producing the opposite of that top piece. And then at the end, I need to jump back. And I'm done. And this is the procedure sum squares, or sums. Or actually, let's call it sum SQ. Now, there are a lot of things I didn't do. Right? I didn't worry about. I didn't have to look at how things were pushed on the stack for the arguments, right? Because we have an agreement that they're always going to be pushed on in the same way. And I didn't have to worry about where I was called from, because we have an agreement that that would be told to me in the LP register, right? Okay, so let's very quickly write the program side of this, which by default I call main. By the way, let me get this in here. Okay, so that's part of the setup for a computer.
Why do you do that before main?
Because I don't really consider it to be part of main. If you were to write a C program, you wouldn't actually store, you wouldn't have to tell it to set up the square. That's something that's normally done automatically for you. Or sorry, to set up the stack. That's normally done automatically for you. So main, what do we do? Well, let's just pick two random values. Pick a number. Actually, let's do 3 and 4 because they will yield 25, and that's one of the Pythagorean triples. Okay. Push. So which one goes first? R2, if you assume that R1 is meant to be the first argument. Yeah, it doesn't matter because the math is symmetric. Actually, let me put a space here. Then we branch to sum square. Now this is now what we're doing right here on these few lines that I'm in the middle of writing. We are satisfying the call-or part of the contract, right? I put my arguments on in reverse order. I branch to sum square and put in the LP register where I'm going to come back to. I have to take care of my own mess on the stack by deallocating those arguments, and then we're done, so we halt. Okay?
Why do you put spaces between the lines?
Spaces between the lines are just for understanding. It is for us humans. The computer ignores them. Now, you can see what I tend to try to do here is put spaces between lines that mean different things. So like these 4 lines here, we can look at and we can just say, actually, let's work on documenting this a little tiny bit. This is call sum square. Right? That's our procedure call. The 4 lines, the whole block, not just that one line. These are just get numbers for arguments. Choose numbers. And then down here we have our entry routine, we have our math, and we have our exit routine. And that's it. And now, hopefully when we run this, we should get a 25 in R0 at the end. By the way, do you guys know how to use the expression thing down here? So if I type in R0 down here, it'll tell me. Actually, let me actually just. I'm experimenting a little bit. Yeah. You can just put any sort of math expression in here that involves the registers and whatnot. So if for some strange reason I was interested in the sum of the values of of register 0 and 1, I can look for that. But we're not. Oh, there's another function this can do, which is to set breakpoints. Here, if I want to see when that second square happens, let's say I want to break when R2 equals, it disappeared.
You could link this so we can actually see what you're typing.
What are you entering?
It's probably not gonna fix it.
It's not being cooperative now.
Can you make the window taller so we can see?
No, you can't. I don't think you can. Oh, yeah, I guess you can. Okay, so you click. I must be using bad syntax. I think R0 equals. See.
Say it early, say it long.
You get 3 tries and
That.
It's a security feature.
Okay. Well, fortunately, I did run it and make sure it worked before we killed it. Okay, so let's very quickly. How are we doing on time? Oh, we have time.
What's the purpose of, what's the difference between the 2 pushes of R1 and R2 that you do? You know how you do one in the main program?
Argument passing and register preservation.
Right. Yeah, those are the 2 different things. One of them is argument passing and one is registered. Let me get out GCDI because that's the closest thing to what we had. No, actually, let's get out square. Oh, I'm surprised I didn't. No, I have squares another procedure. We're doing some squares. It's just going to be plain vanilla squares. Okay, now in here, let's load square. Okay, so you guys have this on the handout. So this is like sum squares, only simpler. So the question Anthony has is, what is the difference between? Oh, darn it. Okay. This is going to be sum scores in about a minute. But it's going to be cold square. I broke the rule. I put it in the wrong place. There. Let's. I like to be consistent from one thing to the next, and one of the things I always do is I actually set the numbers up for the arguments in order, so that it's more apparent that you're pushing them backwards. Push. So we're going to push. Yeah, we really like that R. It's a very loud register. Load. Okay. Almost there. It's much more agonizing when you have to repair it. No, we have to pop these guys. If we merely deallocated the registers at the bottom, we'd just be throwing away their original values. Oh, up top. I'm sorry. Well, my point is still a good one. And okay, what I'm going to do is I'm going to save this. So. Okay, does it look like it used to? It looks good. So then pull the window a little bigger.
Maybe you want to save it first?
Yes, that's what I'm going to do. And in fact, what I'm going to do is I'm going to save it into the shared directory where you can play. By the way, when something goes wrong in the shared directory, you know who accidentally overwrote something. So I'm the only person right now who can save to the shared directory. Okay, so we have our program. I'm pretty sure it's the same, but it's always a good idea to test. And let's put our expression in here. We'll be careful this time. Okay, and click it over. So we got 25. That's a good answer.
How do
do you set the breakpoints in that?
Well, I saved it so I can try. You click breakpoint and you type in an expression that's either true or false. There. So we're going to break when, let me put it up a little further. Oh, we don't need the terminal. It's double equals, it's C style. So this is going to break when r is equals 25. And you can see that right now it's 0 because r0 is not equal to 25. So we're going to go, and it's going to get down there, and I guess it overshoots it by one instruction. But you can see we just did the add, which put 25 into r0. Yeah. Actually, that's true. This value the value in r0 doesn't become available. It doesn't actually become 25 until on this clock tick. So we get it here.
Go back one and show us that it's a 0.
Oh, we can't go back. Unfortunately, you can't step backwards through the machine. Oops. So I don't know what that's going to do now. Actually, I think I just say go and we keep going.
Yeah, except it's going to keep stopping.
Oh, so I can unbreak and let it go. And there we go. So that's how we can use breakpoints. So anything in here that's true or false, where 0 is true and 1 is false. Except I said that completely backwards. 0 is false and 1 is true. All right. Let's quickly do something more complicated.
You didn't answer my question.
Oh, sorry. What's your question?
That's the whole reason you set that thing up. The difference between the two pushes.
Oh, yeah, that's right. I got distracted. Okay. Well, let's change something to make them look a little different. We'll put that in register 3, that in register 4, this in register 4, this in register 3. Okay, now they're different numbers, but this still works. Let's unbreak that. Right? I still did the same thing. Because these actually mean completely different things. They're unrelated. Up here, these two pushes are storing arguments on the stack. And basically, all that matters, the register numbers don't matter. All that matters is that the arguments go on in the order intended. Right? In fact, I can take the second line up there, or the third line if you can, the second line under main, and I can, oh no, I can't. I have to put this line. I can put that line there and take it away from up here. Because it doesn't matter. Right? This will still do the right thing, because all that matters are the values that are pushed. And this instruction does not affect the stack. So we're still getting R4 pushed before R3. But it's not R4 and R3 that we care about, because we can put R0, we can make this be R4 now if we do this. And in fact, the fractal code, if you look through it, they kind of do this, where they load a value in and they push it on the stack. They load a value in and they push it on the stack. And that's all fine. So this will have the arguments. What are the arguments here in order? What's the first argument?
4.
First argument is 4. And the second argument is 3. Now down here, these pushes, in fact, this whole block here, is about preserving the state of the machine in the way it was before you started doing sum square, so that when sum square is done, it can put back the machine the way it found it, with the little exception that you don't have to put back R0, and you don't actually have to put back LP, but you do. Right?
I guess perhaps also to clarify a bit, saying the number of pushes inside your subroutine does not
Correct.
be the same number as the ones up there.
Right. That's a good point. So if I want to do, I can very quickly make that necessary to do. So if I were to use R3 in my computation by, say, doing this, then I'm fine as long as I pop it off down here in the appropriate order at the appropriate time. Because these registers have no, this part of it up here is very, very related to this part down here. Because the top stores the state of the machine, the bottom undoes it. The thing that goes with these pushes up here there's actually two things. We load them here. That's how we access the values. And then we also deallocate them up here when we're done. So those are related. The two pushes, the deallocate. No, I don't. I have some changes I want to keep. So we have to make sure we deallocate them in the main, because main, even though it doesn't follow, even though it's not really a procedure, we do want to keep the stack in good condition. We deallocate our pushes, and down here we can load those arguments that were pushed up here. Right? That make sense?
Yeah.
Okay.
We want to have the stack clean when we're done. Do we care about the register files? Can we just leave stuff in there?
The register file does not have to be cleaned up. But what that essentially means is when you're done, though, none of the registers except R0 should have any important values.
Because it looks like you still have 3 in.
Yeah, but that's fine because they're up here. Now that's something that you don't have to worry about as the program. But for a procedure, you better get them back the way you found them. Okay, so let's do something recursive real quick. Anyone have any good ideas? Yeah, the triangle numbers. Actually, the triangle numbers will be tail recursive. Well, I know nothing is unless you make it. That's why I have the recursive GCD. Unfortunately, there aren't very many good, simple.
We're just adding consecutive numbers.
Some interval from A to B. If equal A, B. Actually, I can show you the compares because we haven't used those yet. If equal A, B, 0. Otherwise, plus A of sum I plus A1 B. Right?
If A equals B, you're setting it 0, not equal to A?
If A equals B. Oh, actually, you should set it to B, shouldn't we? Or equal, or one or the other. They're equal. Let's put B. That way we use a different register in the machine. You're right. There's kind of an off by. It depends whether you want to count A and B as being inside or outside of the interval.
Shy between or is it regular?
Shy between.
Shy between, which is inclusive.
Well, this one's inclusive now. Right? Okay, so let's start. Well, let's not write main. Let's just write the procedure first, because it's a nice way to keep the calling, the caller and the callee separate. But I am going to very quickly do this. Why is it there? And then we'll run down here. Because if I don't do this right away, I will forget, and then we get really weird behavior. Okay, so what did I call it? Sum I. Sumi. All right, so we can go through our standard entry routine, right? Push LP, push BP. This should get to be second nature after a little while. Well, someone guess, how many registers do you think we need? 2? Okay. We'll protect 2 of them. Then we'll see how we do. So the first thing, yeah. Actually, no. I'm gonna use a little trick here, or should I? We can use a trick to get around the base case. Actually, kind of think of it. Let's not use tricks in recitation. Well, the trick is that since our base case is just to return B, we can put B into R0 right away, and we don't need a base case, but let's have a base case. I think I used that trick in one of the pieces of code that I've provided for you guys. So we load the first argument, which is going to be A, into R1. I just like loading them in like that. You know what? I bet we're going to have a good reason to have another. Oh, no, we're not. We're just going to need 2 registers. And we load B into R2. Okay, now what do we do with them? We have to compare them. So compares can't think. Compares in assembly work out to be or rather an if works out to be a 2-line thing. First, we want to compare if they're equal. So that's CMP EQ. There's also less than CMP LT, which is compare less than, and LE, which is compare less than or equal. I don't.
One being the one less than.
Yes, first one being the one less than the second. But for equal, we don't have to worry about that. So we want to know if these 2 values are equal. Now I'm going to use R0 for this, because we don't need R0 yet. And what this is going to do is it's either going to store a 1 or a 0 in R0, depending on whether it's true or false. So if they are equal, we're going to branch if true. This is another way of saying branch BRNZ. But in this case, BT is the appropriate one, and it works. Branch if true, R0, and we're going to go down to the base case, which I didn't put in yet, so we'll just type it in here. So let's actually do the base case real quick. What's the base case? Move R2 to R0, right? Put B, which is R2. Actually, let me write B up here. That's argument A. So move R2 into R0, and then we're done. And then, but this is a little bit of a trick, but not so much of one. We're going to put our return routine down here, and I'll put a little note to self. Finish this. Okay, let's go back up and do the rest of the code. Okay, so if we don't take that branch, then they're obviously not equal, and we have to do some math. So what's our math? Want to add A to the recursive call. Oh no, we have to add 1 to A.
You have to add 1 to A, do the recursive call, and then add R1 and R0.
Right. So there are a few strategies for this, for how we deal with this add 1 to A and then get A back to the way it is. One thing we can do is we can just push A right now and then pop it when we need it later. Okay. Another way we can do it is we can add 1 to it right now and then subtract 1 later. Another way we can do it is we can add 1 and put it in another register and use that. So which one?
Subtract it like
push and pop?
much faster to do to just
That's true. Push and pop tend to be slower for memory accesses, except that in our machine, oh no, there are actually 2 instructions. We don't care about efficiency.
No, but if we did,
Does
you want
it
to
just
use
go
estimate
away?
pushes.
You want to do estimate pushes.
What?
But if we did that, what would be faster, as Chris suggested?
If we-
Or to put it into another register?
It really depends a lot on the architecture. Putting into another register is probably the easiest. It's probably the fastest. But then we have to add another register.
push and pop down.
Here, I'm going to push. I like it because pushing and popping this requires that we really, it's just another thing on the pile of we really have to have good calling discipline. We have to keep our stack correct. So I'm going to do it because it's harder. So we're going to push A because we're going to need to save that. Now don't get this confused with like protecting a register. This is in our procedure. We are pushing it. This is not part of a convention. We're just doing this because we want to. So we push A, so it can have the same value. We're going to add 1 to it. And now we're going to push A plus 1 onto the stack. Right. And this is part of our call. Actually, I probably should.
We'll push out 2 first, right?
Oh, yeah. Good call there. Push R2. Push R1. Branch to Sumi. And store the link pointer. The pronunciations evolve. And then we deallocate our arguments. And we pretend we have the answer in R0 from now on. Which is a fair thing to pretend, because it better be there, otherwise we broke something. That's wishful thinking, but that's a big part of recursion. So now what do we have to do? We have to add A to this. Yeah, so first let's get our A value back. By the way, this pushing and popping things for a little while is a good way to handle if you ever run out of registers. But then again, if you run out of the 27 you have available to you, then you're probably making your code a little too complex. But there are some machines that I've programmed on that you only get 2 registers. So you have to keep pushing things onto the stack. So we pop R1, and now we have our old A back. Now what do we want to do with it? We want to add it to something. Keep writing in scheme. We're going to add R1 to R0. That's where our answer is. And we're going to store it in, well, let's just store it right into R0, because it's our new answer. And notice how consistent I am with the lowercase and capitals. And then what happens? Pretty much. It's time to return. So let's branch down to that tag that I have for return. Yeah. Actually, now why am I branching down to return and not just putting it right here? This is not
Somewhere, the base case will fall through to.
right. I'm just doing it to. It's just kind of a trick to keep the code from getting too bulky, because the base case needs to be able to return as well. So what I just did is I stuck the base case right over top of my return code. So both my normal case and my base case share the same return code, which is fair.
Where do we make as a condition that A had to be equal to or less than B?
Where A had to be equal to or less than B. We just
Larger than B, we have an infinite loop now.
right. Well, we are assuming that the user is being very cooperative.
It would go further. We just add 2 billion numbers together. And we'll get back to that.
Yeah, you're right. We're not testing that. We're just having faith. But the reason is because that actually comes right out of the scheme code. So the scheme code is not completely robust, but the direct translation of the scheme code is this thing. Okay, so let's do a return real quick. We pop R3. No, that's not right. We can pop R3 and move it into R2. Oh, no, we can't, because then we decimate R3. BP. All right. So once again, I'm just looking up here and undoing all the stuff I did up here, and then we jump to LP, and it should work, right? Once we turn it into a program. Oops, that goes up near the top.
You actually change that too?
What?
You actually need to push out too long again?
Yeah, we changed it. It's
We load B into it.
yeah, we load B into it.
All right, let's sum up from 7 to 25.
Okay. Yeah, we have to 7 to 25. All right, so we're going. Actually, now order of the arguments really matters now, because if we get them backwards, it'll go forever. So we're going to move C 7 into. I'm going to put it into R3. And get the cursor out of the way. 25 into R4, and then we push R4, and we push R3. And then we branch to sumi and store the LP. And then we deallocate 2 of them because we have 2 arguments. And we should halt. By the way, what goes wrong if I don't put halt there?
Keeps going down.
Yeah, it's going to start kind of going through this code, and bad stuff is going to happen. Okay. Oh yeah. So you guys want this in shared? What is this one called? Sumi. There we go. Let's see if it works. And our answer, what is our? Oh, Sam, can you do this answer in your head?
301.
Okay. So when we're done, we should see, oh wait, let me fix this. We just want R0. And we should have a 301 sitting right here when it's done.
Actually, 304.
Oh, 304? It's pretty deep. It's oh, let's bring the stack over. Where's the stack hiding? The fun part is to watch the stack. Oops.
Also, when you drag a window, the whole system freezes.
Yeah,
Or robust.
because it causes interrupts. It's a pretty long stack. Look, the program goes down to about, it looks like 2D or so. So the stack is started at the top there. Yep, you can see it coming out. 304. So that's good. You got the right answer.
And Sam is faster than Davidson.
Yes. All right. So now one thing, actually, I didn't mention when it was most appropriate, but that you should have observed is when I wrote sumi here. Not only did I not need main, but I didn't need sumi to do it. Right. This is that funky thing about recursion, that when you write a recursive function, you use it as if it already exists, and the only way to actually make it exist is to assume it already does, kind of. So down here, I just said we're just gonna call sumi, and it wasn't there, or rather, it wasn't done until I did all this, but it still works, and that's wishful thinking. All I have to do to think about how to implement this procedure is to think on just this one level. Right? I don't have to go down the recursion. I don't have to go up to who called me. I push a bunch of stuff on the stack. I have this little contract that I have to follow, and I follow the contract. And as long as I follow the contract, I can be very, I can be sure that everything's going to work out when I need it to. Load my arguments. I do the math that's appropriate to this level. I needed a value calculated by another function. It happened to be the function that I'm actually writing, but it doesn't matter what function this is. I do my math and I return the result. And that's all there is. Now another thing to be careful of is make sure that your pushes balance your pops. That became even more important here when I have this push and pop here. Actually, let me illustrate one more thing. You don't always have to pop back into the same register that you pushed from. It's just a really good idea. Because this gets a little more confusing, right? Oh, no. No, I changed that. No, I'm okay. It doesn't matter, but it is nice. It is good to have consistency. And one of the things that I keep saying in lab is some people like to have 3 registers to do their fractals. Some people like to have 20. And they're either 5. Okay, it's actually 4 or 5. 5 I think is the smallest people tend to do. It's fine either way, but you want to be careful. You want to choose your own conventions that allow you to keep track of things. The people who use 20, they're the people who are doing every time I calculate a value, it goes into a new register. So I always, and I have this big table, but I always know where everything is, and I can get anything I want that I've ever calculated. That's fine. It's actually not inefficient until you start getting too many, more registers than you actually have. On the other side, some people are comfortable with being able to move values around. They can keep track of, well, I had A was loaded into R1, but then I pushed it. Well, where did it? Yeah, there. Then I pushed it on the stack, and when I popped it out, I decided, well, I want to put it in R2 now. That's fine. But be careful. I prefer this method, personally. That A went on in R1, comes out in R1.
If the answer is 304, why is R0 listing 130?
It's in hex.
Of course.
If I click it here, I get 130. Okay, so actually, for one thing I was somewhat interested in, today I was fixing up the code. By the way, the old fib-r, the one you guys have on the handouts, some of you guys I mentioned this to, but if I didn't mention it to you, did any of you guys figure out what's wrong with fib-r? Okay, it violates the calling conventions. It's a ugly piece of code. So I rewrote it. The fib-r that's that's on the system now in the shared directory is a nice, elegant, and it looks, it has this style that all my programs have. And this one works, and it follows calling conventions. Specifically, the old fib-r was not protecting registers, mainly just because you actually didn't need to. But that's not a good excuse. Right? You guys know that, because when you write a procedure, that procedure might be taken and put into someone else's program, and it better work no matter what environment it's in. The old fib code will not work if you transplant it somewhere else. So there's a new fib code. I wrote recursive Fibonacci, but my challenge, because I was sitting there and I thought it would be cool, is write iterative Fibonacci that will calculate, I don't know, pick a number, the fib of 24 in as few cycles as possible, but that doesn't violate the contract. That's just my challenge. If you have extra time, and I'm going to make one because I think we need to, I want to fill out things, but calculate Fibonacci of 24 in as little time as possible. Now, another thing is you can't just have it spit out the 24th Fibonacci. It has to compute it. Because I knew some of the troublemakers were thinking that. But it has to be able to calculate every Fibonacci number, but for the metric, the Fibonacci of 24 is in as few cycles as possible. Right? And you can't just detect 24 and spit that one out and do everyone else legitimately. Don't worry, I know all the tricks. I'm a troublemaker too. Okay, and that's it. Does anyone have any questions about this stuff? This stuff's starting to make sense? It takes a little while. It's a different way of programming, obviously, than Scheme. Though after a while, you guys should start being able to see the similarities. I mean, you should already be able to see that we can take Scheme code and turn it almost directly into assembly. But being able to look, most of you guys know pretty well how to look at the Scheme code, and it really helps to get a good, just practice getting used to looking at the assembly and saying, well, I know that, oh, I made this ugly.
Are we going to write more programs?
This, probably. But I know that that's a procedure call, right? And you don't have to worry about the details.
Don't ask that kind of questions.
When you highlight stuff, something flashes.
Blinking at you.
I don't know why.
It's probably
All right.
drawing the cursor.
Yeah, it's doing something. All right. So any questions about anything?